Okay, let's continue our discussion on deflection. So there are two types of deflections we have to consider, as I have shown you on the table in the previous video. So the first one is the immediate deflection, which is a short-term deflection, and the second one is a long-term deflection. Okay, so these deflections are different in terms of their nature, because the immediate deflections are actually called the elastic deflections. So these are the elastic deflections, while the long-term deflections are actually time-dependent deflections, which are based on temperature, shrinkage, and creep. Okay. So for immediate deflection, the following equation is applicable to beams and one-way slab, which is actually very accurate if we are considering beam types in terms of simple, continuous, and cantilever beams. Okay, so we actually have a lot of methods in computing deflections, starting from classical methods like Castellanos theorem, virtual work method, etc. But the most or the simplest way to do it, especially when we're talking of these three types of beams, okay? So the types of beams that this can handle are the simply okay, the simply supported beam, the continuous beam, okay, and the cantilever beam. Okay, I'd like to make an abbreviation of this so as to facilitate our discussion. So when I talk of SS, we simply refer to the simply supported. When I talk of continuous, we might as well use the abbreviation as because these are both on the letter C. Okay, so I'll just make it distinct. Okay, so for continuous, we can use CTN. Okay, CTN. Okay, this is SS for simply supported, and for cantilever we use CTL. Okay, so just to distinguish, SS beams, CTN beams, and CTL beams. Okay, so just for the sake of discussion. Now, let's look at the formula. The formula is quite easy, so we only have to memorize a factor here, which is actually a factor for a deflection applicable to point loads at the midspan. Okay, so these are concentrated loads at the midspan. Okay, so this is actually a factor to memorize. It's a 5/48. So this K here is another factor to capture the type of support. Okay, so if it is SS, CNT, or CN sorry CTN or CTL. Okay, so take note of my abbreviation. And all you need to memorize is the ml squared over EI, ml squared over EI. Where in this part here, class, is simply your curvature. Okay, you term this as your curvature. M over EI is actually your curvature multiplied by L squared. Okay, so ml squared, and the totality of this is makes uh, your deflection, immediate deflection uh, value. Okay, so this ml squared over ECI is the term that is the most important, that will give you a value for your immediate uh, deflection. Okay, so it's not very difficult to really memorize it, I think. Okay, so take a look at this part here. I told you about the K's. Okay, the K values is 1 for simply supported. Okay, so it's SS again. 12 over 5 for cantilever. Okay, and 1.2 minus 0.2 MO over MM for continuous, CTN. Okay, so just look. So what is the difficult part here is on the continuous continuous support type. Remember that these are now your types of support. Okay, and we're going to look into the details of what MO and MM is, aside from M, which is a part of your immediate deflection equation. Okay, so for M, your M value is simply the mid-span moment for the simple and continuous beam. Okay, the moment diagram for SS is simply a parabola like this. Okay, so this is your M mid-span moment. For continuous, your moment diagram is shaped like this. You have a negative part there. Okay, so this is now your mid-span moment. They are different. Okay, they are different in terms of formula. Okay, and for your cantilever also, the moment diagram is like this. Okay, actually this is a negative. Here you have a positive moment at the mid-span. Here you have a negative moment support. Here you have a negative moment support. Of course, we neglect always the sign, just as I have told you. The sign here only indicates the nature of the bending, if it is positive or negative. It's nothing to do with the absolute value, the magnitude of your deflection. Okay, so we often neglect this negative sign, okay, or ignore in the computation. Okay, so what is MO and MM? Okay, MO for this simply supported is equivalent to MM. Okay, so simply because the moment, the simple span moment here is equal to MO. What is MO? It is WL squared over 8 for uniform loading. Okay, so for cantilever, it's different. Okay, so your MO for cantilever is not equal to M at the midspan, because MO is WL squared over 8. It has a value equivalent to this. So this is your MO there. Okay, here this is your MO. Okay, now for cantilever there's no MO here actually, because this is a negative value. We don't have to worry about it. Okay, and what is MM? MM is the net moment at the midspan. Okay, here the net moment is still the same. Is still equal to MO. But here, the net moment is no longer the same, because your net moment MM is equal to MO minus this average value here. Okay, so we have an average value that appears here, M average, that we're going to compute on the basis of the negative moment. So minus M average. Okay, so this is how we deal with M and MO and MN. While these two here are simply the properties of your beams. Okay, so we will deal with this later when we solve problems. Now let's talk about EC and IE, which are the properties of your beams. So these are called actually the flexural rigidity of the beam. And the flexural rigidity affects the accuracy of the computation for deflection, since it at load increments the value of the flexural rigidity varies depending on the nature of the section and the reinforcement at that instant, and at different locations where the deflection is determined. So the following observations are noteworthy, especially for sections where T-beam formations are likely to occur. And that is for a slab beam floor system. Okay, for your information, the modulus of elasticity are described in this manner. No? So it is more variant than F prime C, meaning to say it changes, no? Just like the COVID virus, so it changes from one variant to the other. So it's accurate only to about plus or minus 15 to 20%. So the range is quite big, no? So plus or minus, meaning to say if you have here the positive side, this is from 15 to positive 15, or even so it is from negative 20 to positive 20. Okay, so it's actually very inaccurate. So affected by creep and shrinkage. What is creep again? Creep is the effect of sustained loadings on deflection. These are due to sustained loads, while shrinkage is due to the presence of moisture. Okay, so this is presence of water. So it will expand, it will contract in the presence of water, while for creep it will deflect or not, depending on the sustained load supplied. And what are the sustained loads? I will dig deeper into this later. Okay, so the moment of inertia, on the other hand, varies considerably along the span, and it depends on the reinforcement. Okay, so and it also depends on the magnitude and sign of the bending moment. So let's take a look at the figure here for us to be able to see. So the moment of inertia class at each section is varying because of the presence of the cracks. Here, the cracks are at the top. Here, the cracks are at the bottom. So if you have a crack section here, your beam will be shaped in this manner. Okay, so your beam is like transformed section. It's like this. While here, your beam is shaped in this manner. It's a T-beam. It's a T-beam. It's shaped like this. Sorry, I can extend. Okay, we can extend this to this one. Okay, so the property of this section is different, very much different. So what moment of inertia are you going to use if that's the case? So this requires a lot of experiments and a lot of work to recommend a formula and equation to determine the value of your effective moment of inertia. So we now make use of the term effective moment of inertia, okay, to address the problem of what moment of inertia to use because of the variability on the property of your beam section by section. So this figure shows us the complexity of calculating the flexural rigidity, not to mention the effect of reinforcement variation along the beam span. Okay. Okay, so how do we compute for the effective moment of inertia? So the ACI now gets again into the picture of guiding us. So due to the difficulty in choosing the representative value of I along the span, ACI recommends the use of the following equation computed as mid-span value or an average value of the support and at the mid-span. Okay, so what ACI did is gave us a formula for taking into consideration the effective moment of inertia at the support and the effective moment of inertia at the mid-span, and then we take the average value as recommended by ACI. Okay, so this formula actually gives us a combination of the, once again, IG, this is the gross moment of inertia, and the cracked moment of inertia. Okay, so the crack effect of the section actually controls the value of your effective moment of inertia, but it has to be less than or equal to the gross moment of inertia because we cannot exceed this for safety reasons. Okay, so this equation 9.7 of the ACI, where MCR is the cracking moment equivalent to FCR IG over YT. FCR is the modulus of rupture equivalent to 0.70 squared of FC prime. So in our previous lectures, I used a 0.62. Here we round it up to 0.70. Okay, so we use this one instead of this one here. It's not that this is wrong, only for preference we use 0.7. So IG is the gross moment inertia of concrete, MA is the applied service load moment. Okay, so the service means you will be using WSD loads, okay, service loads. So meaning to say these are unfactored loads. Okay, ICR is the crack transform moment of inertia, and MCR over MA is the moment ratio. So note that equation 9.7 is intended to be calculated at the location of the maximum moment as a single value for the entire span of simply supported beams. Okay, so for simply supported, you just get IE at the mid span. Okay, mid-span. For continuous beams, we can also use a single value between points of inflection for continuous beams. Okay, so when you say between points of inflection, so this is for continuous CTN, so i.e. between PIs, okay, point of inflection. For cantilever, of course, we use the support. Okay, so these are the effective moment of inertia to be used in equation 9.7 as summarized here. Single value for continuous mid-span and cantilever. IE is equal to IEM. So again, this is for mid-span and value and continuous beams. Okay, simple and continuous mid-span. And for IEM, at cantilever, we use the support value. Okay, this mid-span, this support. Okay, so why is it that a while ago I told you it's between point of inflection? So the assumption is that your mid-span, okay, MS is in between PIs. Okay, so for the simple average, we have to take note that this is only applicable for simple and continuous. For cantilever, it is not used. Also for the weighted average. Okay, so this is the simple average IEM plus 1 half IE1 plus IE2. And for weighted average, this is 0.70 IEM plus 0.15 of IE1 plus IE2. Both end continuous, and one end continuous, we have 0.85 IEM plus 0.15 IE1, where IEM's the effective moment of inertia at mid-span and IE1 and IE2 are the support. Okay, left and right support. So these are the left and right support. So if you have a beam which is this long, you have three moment of inertia. One is the mid-span. This is IE at first support. This is IE second support. Okay. Okay. So that finishes the lecture on immediate deflection. So again, I will be looking into some of your concerns first before we proceed with the ACI long-term deflection. Okay, so I'll see you in my next video.